Alright, today we're going to talk about our sun. Now, our sun is just a star. It's like many other stars in the universe. It's actually a medium sized star with medium temperature, with medium energy output, so it's not that unique. What is unique, to us at least, is without the sun, there is no life on Earth. All the energy that you have right now comes from the sun in one form or another. Now, our sun is a star, just like any other star universe, but since it's so close, appears to be very, very bright to us. But like I said, it's about medium brightness even. Without heat and light from the sun, there would be no life on Earth. Now, the heat only happens once the light from the sun enters our atmosphere. The only thing that travels in the space between the sun and the Earth is light particles called photons, and some solar particles which interact with our atmosphere. There's no heat. I mean, if you're out in space, you would freeze to death, even if you were very close to the sun, because, well, there's no heat there. It's only light that gets to travel through space. Now, the sun is a huge ball of gas, technically plasma, which is the fourth state of matter, which is very excited gas, made mostly of hydrogen and helium. And most stars are made of hydrogen and helium. Hydrogen is the number one element in the universe. The sun doesn't really burn, but instead there's a conversion of hydrogen to helium through nuclear fusion. So we take our four hydrogen atoms, and because they're moving around really, really fast, they get really, really excited, and they get pounded together into one atom. They form a single helium atom. And in this process, we lose mass. The mass of the four hydrogen is the mass of the four hydrogen is more than the mass of the one helium, and the lost mass is converted into energy. Now, of course, this finally explains to you the most famous physics equation ever, which we attribute to Einstein. E equals mc squared. E is the energy, m is the mass, and c is the speed of light. This is actually the equation we can use to calculate the loss of mass of the sun to the amount of energy being produced by it. And now, this nuclear fusion that takes place happens in the center of the sun because there's so much gravity there, there's so much forces pushing the atoms together. It's very, very difficult to push the nuclei of atoms together to combine them. And so this only happens really in the sun or in some places on Earth where we produce giant magnetic fields or use very, very powerful lasers to do this. So the sun is not on fire. It's not like a piece of wood that's on fire. Instead, it's the process of nuclear fusion that produces the light and the energy that provides all the light and energy in our solar system. Now, the sun is 99% hydrogen and helium, with the remaining 1% made of many, 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 many other elements. Now, the amount of calcium in the sun can be extracted and can be made into another Earth. And the amount of gold can't make it an Earth, but we could gold plate the Earth with gold 100 meters thick. So you kind of get an understanding of how much material is really in the sun. The sun is huge compared to the Earth. Now, the formation of the sun happened about 4.6 billion years ago. Began as a cloud of dust and gas, and gravity pulled it inwards and began to rotate. Temperature of the ball grew as it condensed, and as it increased to 18 million degrees Fahrenheit, which is a very necessary temperature here, fusion occurred and the sun was born. The sun will only last probably for another 5 billion years. Now, I know this brings the total lifespan of the sun to about 10 billion years. Now, this is actually, again, medium. Now, if our sun was much bigger, much hotter, it'd actually burn out a lot sooner. If it was smaller, it actually could last longer because it all has to do with really the temperature, because that's the rate at which it's producing the energy. And so we can look at the brightness of our star and figure out how quickly it's producing energy. Now, the surface of the sun is a very active place, and we have certain satellites that are in orbit around it, which take very close-up pictures of it. And, I mean, it's like flowing lava in a sense, but you have these beautiful arcs, and you have material being ejected, you have explosions, you almost have like tsunami waves on the sun. Now, occasionally we see a darker spot in the sun, which we call a sunspot. It's a region on the sun's surface that is marked by a lower temperature than its surrounding and intense magnetic activity, forming areas of low surface temperature. Although they are still blindingly bright at temperatures of roughly 4,000 and 4,500 Kelvin, the contrast to the surrounding material at 78 Kelvin leaves them clearly visible as dark spots. And we can even see this in the classroom by using the red telescope. We can project an image onto the ceiling of the sun, and we can actually see the little dark spots. It's just because it's a little bit cooler that it seems darker. Now, sunspots are often related to intense magnetic activity such as coronal loops and reconnection, material that gets ejected out from the sun and comes back in. Now, there is a 11-year pattern for high activity to low activity of sunspots. So let's say this is now. In 5.5 years, we'll hit a low spot of activity where there'll be very few sunspots and the sun's surface will be relatively quiet. Then our 5.5 years after that, we reach another high point. And so it's 11 years from high point to high point or low point to low point. And we are nearing a high point in the activity of the sun. Now, the sun's surface does impact us because as the more sunspots happen, that means it's more active, which means it's also can eject more material, which can travel through space, interact in our atmosphere, it can actually interfere with satellites and knock them out. It's also actually caused power outages on Earth by causing power failures in certain electrical production plants. So we do pay very close attention to the high activity of the sun. Now, this was a little animation. You can see as the sun rotates, the sunspot moves with them. They're on the surface. And as they move, the sunspots change in size and shape. They get bigger, they get smaller. And they actually help us understand how quickly the sun is rotating. Now, this is another image showing you it was a explosion kind of on the sun. I'm going to go back and come back to it. And that is actually, there's a lot of images like this where you see the sun's surface exploding outwards. And you can see actually a white spot on it now. And that's because it's a hotter spot, but we'll oftentimes see a dark spot with it. Now, the sun is made up of different components. So this is a very basic image showing you the different parts of the sun with the core in the center. Here's our core. And then we get kind of two layers outside that, the radiative zone, the convective zone. Then we get the surface of the sun, which we call the photosphere. And then the chromosphere is a small region outside of it, and then the corona. Now, the corona is the outer layer of the sun's atmosphere. It's extremely hot and thin and only visible to us during a solar eclipse or with special satellites. During a solar eclipse, you'll see a very, very bright kind of halo around the sun, and this is the corona. Now, corona means crown, so this is kind of like the crown of the sun. Uh, think about this almost like the atmosphere. Now, the chromosphere is kind of the bottom layer of the sun's atmosphere, so it's just outside the surface, has huge flares and loops, shoot electrically charged particles through it, and these can travel to Earth, and we can see auroras. Some of these loops are so large that the Earth could actually pass through them. I mean, we're talking about the sun is a big place. Well, the big activity happens on them too. Now we get to the surface of the sun, which is the photosphere. Now, photo means light. And of course, you know what sphere means, so it's the light sphere. Because this is where most of the visible light from the sun comes from. This is what you see if you were to look at the sun. We only see the other parts when this part is blocked out during an eclipse. So photo means light. So this is the light sphere. Sunspots, of course, occur in 11-year cycles. That is a very important thing to remember. Now, the inner part of the sun, going from the core outward, the outermost part of the inside is the convective zone, and this is where the energy goes from really radiative zone outwards through convection. So we get material rising and falling because of differences in density due to differences in temperature. The radiative zone is where energy radiates outward from the core into the convective zone. And of course, the energy comes from the core, which is where the atoms of hydrogen ram into each other, causing nuclear fusion to occur. Now, the process can take more than 1,000,000 years to get the energy to the surface from the core. So this is a very slow process. And the reason why is because it's very, 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 very dense. I mean, the sun is very, very dense in the middle. And so it takes a long time for energy to travel outwards. Some basic measurements of the sun. Its mass is about 330,000 times the Earth's mass. Its diameter is 1.4 million kilometers, or about 109 times that of the Earth. So you could fit almost 109 Earths side by side inside of the sun. It said you can fit a million Earths inside of the sun, pretty much. Rotation, it takes about 25 Earth days for it to rotate once. Its surface gravity, if you could stand on the surface, which you can't because it's plasma, you would burn it up instantly, is about 28 times that of Earth, and so that's due to the increased mass of the sun and the increased density. And it's 150 million kilometers away from the Earth, which we relate to one astronomical unit, and that's just the average distance between the Earth and the sun. Now, of course, our distance changes, but so little it doesn't really matter. And just so you remember, January we are closest to the sun, and in July we are farthest from the sun. And like I said, it's a very small difference. Doesn't really matter, but we do move closer and farther away